thank you very much for having me, and thank you for the kind introduction. I really appreciate that. And thank you for coming today. It's really nice to see some familiar faces and lots of unfamiliar faces, so thank you. Before we begin, I wanted to give you a brief overview of what I've been interested in for my research, so it can frame this question that I'm posing of, will snow help or hurt sea ice in a warming climate? I'm too quiet.
So I'm trying to move it up a little bit.
Okay. Both of them?
Just this one. Just the other one. Better?
Better? Okay. Just go like that if I need to speak louder. Okay, great. Thank you. All right. So what have I been doing for the past 10 years or so? It's been research on snow and sea ice, and I've been really fortunate to be able to straddle these two environments of remote sensing and field observation, so getting a healthy mix of how I can bring stuff that satellites see in context of what we see on the ground. And I've really been focusing on snow on top of the sea ice, and sometimes how sea ice melts as well, and the processes in the atmosphere that affect snow and sea ice. More recently, I've been working with modelers, and so this has been helping develop models, to represent processes in the models, and also to evaluate trends in the models. And I'll show a lot of that work today and put it into context. But the whole point of this talk is to go over snow and why it's so important for sea ice and how it may affect sea ice in the future. So why do we care about snow? Well, first, I want to tell you what my goals are of this talk. If we can get to any of these questions, if you can walk away from this talk and answer any one of these, that will be a huge success in my mind. So if you could answer how snow is good and how it can be bad for sea ice mass balance, that's a win. I'd like you to understand what our limitations are in understanding how snow functions in the sea ice environment and how we can make progress in the field of snow research. How can we move forward with the science and use models and observations together in a safe way? And that will make a lot more sense as I keep talking. And then lastly, and maybe this will be some of the more exciting stuff, what's the low-hanging fruit in this area? Where are future directions that we can go with it? And I'll outline those as I continue this presentation. All right, so snow. Why is it important? And I think a lot of us know this reason, but it has a very high albedo. It is one of the most reflective surfaces on our planet, reflecting the majority of solar radiation back into space. So if we didn't have snow, the Earth would gain solar radiation and warm. It's pretty clear cut. But we hear a lot about the ice albedo feedback, and in fact that's what we hear most about when we think about global warming and changes in the Arctic. So is there such a thing as a snow albedo feedback on sea ice? You know, this is a pretty straightforward question to ask, but perhaps snow doesn't really matter for ice in this context. And actually, it does matter. So I want to give you an example of some data that we collected from 2011 about why snow is important for this thing called melt pond evolution. What you're seeing here, or maybe I should point here, this is a melt pond. This is melted snow and melted sea ice, and this water is pulled together in this beautiful blue puddle. And these are covering the sea ice surface every summer, the Arctic sea ice surface every summer. And they do make a big difference to the surface albedo of the ice cover. And when they form is really dependent on the air temperature and how much snow there is. So in the Arctic, we're actually in a really unique environment where we have two types of ice there. We have old ice and we have young ice. So old ice is stuff that survived multiple summer melt seasons, and the traditional thought is that it usually has a thick snow cover on top of it because as soon as snow falls, there's something there to capture that snow. Young ice, on the other hand, we tend to think that it has less snow on top of it because if it's not there, if it's not yet formed, all that snow is going to fall into the water and melt. But what we found at this site is melt ponds were forming first on the old ice by 3 weeks compared to the young sea ice. So what I'm showing is the area covered in melt ponds of the ice and through time. And the red is for the old ice and the blue line is for the young ice. And so there's a 3-week difference here. And this is actually a pretty important difference in timing when you think that an ice cover covered in melt ponds is only reflecting 40% of that solar radiation compared to something snow covered, which would be about 85%. So why is this? Well, the point of this talk, and you can probably guess, is it has everything to do with the snow cover. And what we found was the snow on this old ice in this area was extremely thin. It was much thinner than 10 centimeters. And 10 centimeters is a magic number. Anything thinner than this is optically thin, which means you can see the underlying surface of snow that's thinner than 10 centimeters. And in fact, there's a large part of this area of this old ice that was snow-free. And I'm not sure if you can see this as well, but there are these darker patches here which are actually completely free of snow. And if you can see that with your eyes, there's definitely going to be a lot more solar absorption happening in those areas. They're going to warm, and they're going to melt faster. So in this sense, snow is really important, and thin snow can be a pretty bad thing for sea ice. But is thin snow always a bad thing for sea ice? And the answer is no. Thin snow can be a really good thing for sea ice depending on when it's there. So what I'm going to show here is an example of what a thin snow cover does over the course of a sea ice growth season. So this is data that was collected near Point Barrow in Alaska, the northernmost point, in this area called Elson Lagoon. So it's this little area that's surrounded by land, and what's special about that is the ice is contained. It's not moving with the ocean currents or wind. It's fairly static. And this is a perfect place to go for a thermodynamic experiment because you have no dynamics going on. So what we did is we took a lot of snow depth measurements and a lot of ice thickness measurements along a survey line. This was about 500 meters in length, and we have multiple lines like this, and every single one showed the same pattern, where you had a proportional relationship of snow thickness and ice thickness. Where the snow is thinner, the ice is thicker. Where the snow is thicker, the ice is thinner. And this has everything to do with the amount of thermal conductance through the ice cover and through that snowpack. So it's quite proportional. And this isn't a unique thing for that year. We've gone back time and time again and see the same thing time and time again. It's a really effective insulator for the sea ice environment. Okay, so why is this important? Well, as Arctic sea ice is thinning, which we have really nice observations from submarines and satellites over different parts of the Arctic that show a clear trend that ice has thinned over the entire Arctic. There's this question that we can ask, is sea ice going to become more sensitive to the snow cover on top of it? And a really nice example of this is from a modeling study by Gary Makett in the late 70s. Is this model representation of thermal conductance as a function of snow thickness and ice thickness. So here on the left is snow thickness, on the x-axis is ice thickness, and these numbers represent the thermal conductance through the ice pack and the snow cover. The main takeaway is that a little bit of snow can go a long way in insulating the ice, especially for thinner ice categories. So if you look here, this is a number that's 20 in case you can't see in the back. And it goes to 1, and that's just a 30 centimeter difference in snow cover for very, very thin ice. So perhaps snow will become more and more important as ice continues to thin and as the climate warms. That's an open question, and that's something I'd like to look at in the future. But as ice has thinned, there's also been thinning in the Arctic snow cover on top of ice. So these are going hand in hand, and so this can come about in 2 ways. You could be having a top-down effect, so perhaps there's less snow happening, or less snowfall, or maybe there's more rainfall. Or maybe the changes in the ice are influencing how much snow can accumulate there. So what we found in this analysis, we cobbled together a lot of data sets, some being from these drifting ice stations, which are shown in blue here. We have a lot of measurements from aircraft, from Operation Icebridge, which is shown in red. And then we have a bunch of data from these drifting buoys shown in yellow. And so we strung these data sets together to look at the trend and found that indeed this is a decrease of about 3 centimeters per decade in this western Arctic area. So when I say Western Arctic, I'm just talking about these western longitudes. I'm not talking about the eastern part of the Arctic. So what's happening? Is this top down or bottom up? Well, we tried to look at both, and what we found was a really interesting relationship between the timing of sea ice freeze up and how snow accumulates and when it accumulates. So on this upper left-hand figure, this is the date of sea ice formation. The blue represents September and the red represents about October, November. So there's a really big difference in when sea ice forms in the Arctic, and we found that the trend in sea ice freeze up is later and later, and this coincides with the same areas that are losing snow. So the biggest loss of snow happens in the areas with the latest date of sea ice formation. And this starts making more sense when you start looking at the snow accumulation rates of sea ice in this area. So on the bottom is snow accumulation for each month, and the red is from these historical data from these drifting ice stations, those blue dots that you saw earlier. And the contemporary data is the same from IMBs, or ice mass balance buoys. And I wanted to compare the contemporary period to the historical period. So the historical period being back to the late 1950s, contemporary being 2000 to 2013. And the big takeaway here is we were just looking at spring snow depth distribution, so this March-April period, and we found that the total accumulation really wasn't that different between the two. And we found also that most of the accumulation is still happening during the autumn period. So if we have less and less ice, or if it's forming later and later, it's essentially missing that snowfall during that peak snowfall period in the Western Arctic. So that was a big takeaway here. And we can really say that this is a bottom-up approach. So when you think about snow in the sea ice environment, it's not just a static thing, it's tightly coupled to the ice underneath it. Okay, so I said we don't know what's happening in the Eastern Arctic, and that's because snow depth observations are very sparse. We really have a poor record of what's been going on in other parts of the Arctic, and it makes it really difficult to say anything about trends in snow depth on sea ice. So we have to rely on models for this. What I'm showing here is all publicly available in situ data or aircraft data of snow observations, and the background is modeled snow depth. So we're really relying on models to fill in this picture to understand what's going on. That's essential, actually. But models are showing mixed results of showing mixed results that snow is increasing and sometimes snow is decreasing in the same area. So how do we know which model to trust? Well, we just can't because we don't have enough observations to know what's true. And they differ because they treat their physics differently. These different snow processes that are occurring can be a crude simplification or they can be extremely sophisticated, but we still don't know which one is a better model. Why is this? Why is snow so difficult to model? Why is it so difficult to get observations in these locations? And why can't we just make this model function in a more realistic way? So yeah, this is what I want to focus on for the next few slides because I think this is really where we can make a lot of headway in this field. So snow is really difficult to represent, to understand, and to collect observations for because it's tightly coupled to the atmosphere and sea ice conditions. The atmosphere is constantly changing, and so is the sea ice environment. So because of this tight coupling and because snow just naturally changes by itself, metamorphism of its snow grain crystals, it is also constantly changing in space and time. So that makes it really, really difficult to take a single set of observations and apply it to another place or to another time. And that's something that we have to take on board when we're evaluating models with observations. So what are some of the other challenges? Well, like I was saying, the representativity of these, or the representation of these observations, are they going to make sense in another location in another time? And I think what's really important is where were these observations taken? So depending on their geographic location, this really controls what snow processes dominate that area. So I'm showing a pretty complex picture of all these different processes that affect snow, but also affect sea ice. But depending on which one dominates is really dependent on where it is in the Arctic or the Antarctic and what the atmosphere is doing. So this is an added challenge for collecting observations that are representative, that we can assess models with or improve models with. Also, there are large uncertainties in observations that we need to take on board. We would go out in the field and take a bunch of snow depth measurements and then hand them over to modeler and say, here you go, do your science. And that's not really how it works anymore. And I'll show ways that we're really going to improve this strategy of bringing models and observations together. Okay, so we've spent a lot of time talking about why snow is important, and there's been a lot of meetings on how to progress the science of snow on sea ice. And one key message that I wanted to share with you, which is direct from the community, for many members in the snow on sea ice community, is that we have to bring modeling and observational efforts together. We have to integrate that in order to make progress on these processes. And a really valuable way to do this is to use schematics like this complicated figure, and isolate different processes as a roadmap for low-hanging fruit. So we really don't know how important each of these processes are. We think they're pretty important. We've surveyed a lot of snow on sea ice experts, but we don't know how important they are on a climate scale. If one of these processes goes away, will it have a ripple effect on the conditions in the Arctic or the Antarctic? So there are ways that we can integrate modeling and observational work, and I think a really nice case example is this campaign called Mosaic. So some of you may have heard of Mosaic. It is an expedition where they're freezing a ship in the middle of the Arctic for an entire year. They'll drift with the ice pack, and they're taking continuous observations of the atmosphere, of the sea ice, of the ocean, of the biology, and how it all functions together. But a lot of the work and the strategy that went into that was guided by model experiments. So a case example is we found that the distribution of snow is really important for how heat is conducted through the ice cover. If you have a uniform cover of snow, it's going to do something completely different to the heat exchange than a checkerboard pattern of snow. And that has an effect on sea ice growth. So we've designed a field experiment to sample the snow in a coherent pattern that we can match to the model, that makes sense for comparing with the model and improving the model physics. So that's a really nice example, and if you're interested in that, I'd encourage you to go to the website to learn more, because there's some really beautiful images from being frozen in there since October. Okay, so another strategy is to use observations to guide model experiments. A really nice case example is one recently where my colleague Dave Bailey and I were looking at data from this drifting ice camp. We're looking at the area that snow covered as a function of the mean or the average snow depth. This is how the model parameterizes albedo. And if you match that to a different field camp data set or to a different location, you can throw the albedo into a completely different state. And we actually melted all the Antarctic sea ice, even though we better matched the Arctic sea ice field data set. So finding out which parameters are really, really sensitive by evaluating them with observational data is really key and really helpful for designing future experiments to gather more insightful data. And the last one is kind of a mix of the first two. It's really synthesizing model and observational results across multiple scales. So when you have point observations from the field, how to relate those to a model grid cell is really important, and I think that's often overlooked. And the point I'm making here for Mosaic and for the schematic is it's really powerful to be able to scale up, and that's a really valuable thing that Mosaic is achieving with airborne measurements to link the ground measurements to the satellite measurements. Okay, so that's a big overview about snow. Now I want to get into more of the results of more recent work that we've been doing, and it's really going to hit these last 2 points of using observations to guide a model analysis and synthesizing model and observational results across multiple scales. And this is motivated by snowfall and discrete accumulation events that happen in a snow cover. So what I mean by that are these highlighted areas where you have jumps in the snow depth over time. We were curious, what causes these? We actually don't know. Of course it's snowfall, but how does the snowfall get there? What mechanism is causing that snowfall? Is it just drizzly snow, constant scant snowfall, or is it massive events? And how does this vary across the Arctic? This was really motivated by data from these ice mass balance buoys. I mentioned them before, but I wanted to show you what they actually look like because they're interesting. This is what they look like now. You have this data logger here and a battery, and you drill a hole in the ice and put a thermistor chain down so you can look at the the temperature evolution vertically within the snow cover and the ice cover and the ocean. And you have these pingers, or these acoustic sounders on top and on the bottom. So this one's looking at the bottom of the ice cover. This is looking at the top of the ice surface or the snow surface, depending on if there's snow there. And you can check these changes over time. So over time, you can get snow accumulation if snow is falling and landing on the ice, or you can get snow melt over time if the snow melts away, because you can get this distance information. So what really intrigued me about this data set is I collected a whole bunch of buoy data together and kept seeing this distinct pattern between two regions of the Arctic. When you look at the Beaufort Sea region, so vaguely this is the region, and the North Atlantic region here, the way snow accumulates is very, very different between these two areas. On the left, you can see it's just kind of a steady snow accumulation. There's not much happening over the winter time. But in the Atlantic, there are these massive jumps over time, and it just seems to be continually growing in thickness. So I wanted to know what's driving these differences. What are the key things that we can look at that can try to provide insight on what causes snow accumulation, and how can we better represent those in models? So that's what we did, but we related it to some of our previous work, and we started with cyclones. So why cyclones? It snows a lot when a cyclone event happens. They're easier to identify in the data that we have in the Reanalysis products. They are always present in the Arctic at least once. They seem to be happening year-round at least once. And honestly, I was just curious about these fast-moving features from my earlier work as an undergrad. We would see these features that had these comma-shaped patterns in passive microwave data. And this is supposed to be sea ice concentration, but you can see weather has a negative effect on the retrieval. And I wanted to know more. How are these affecting the snow on the sea ice cover? So the approach to this work is we broke this down into a regional analysis and also a seasonal analysis of the snow accumulation period. So this is from September going into May. There is snow that falls and accumulates outside of those months, but this is really when the snowpack builds up most rapidly. And we're looking at nearly 40 years of data to evaluate trends and changes over time. And lastly, we're looking at this in a way of using reanalysis data with in situ data. We didn't come up with our own algorithm. We used this cyclone tracker from the Melbourne University, but we applied it in an Eulerian framework. And the reason for doing this is if you're an ice parcel and a cyclone double backs on itself, you would experience two events. And that's why we wanted to use it in an Eulerian framework rather than a Lagrangian framework. Okay, so our goal here, our objective, was to quantify the contribution of cyclones to snow accumulation on sea ice. How important are cyclones? And we did this by using error interim reanalysis data, and I'll get into that choice later on in the talk. We use this thing called snow depth reconstructions. And another way to think of this is it's a way to model snow depth on sea ice. Because we don't have a lot of observations of snow, we have to model it, remember? So we're tracking these ice parcels as they drift throughout time. We have satellite data that tells us where it is. And we can accumulate snow on that ice parcel over time using reanalysis snowfall. We convert the snowfall to snow depth using a climatological snow density. The thing about this approach is we aren't losing snow in any way. We don't account for ice melt. We don't account for snow blowing into leads. We don't do anything of that. We're keeping it very simple, which is okay because our question is really about how snow accumulation happens, not how it melts. And if you're interested in seeing how this approach works and how it compares with observations, you can always see this paper by Ron Kwok that shows something similar to this, where it does have a good agreement with observations as far as we can tell. Again, who knows what's happening in the eastern Arctic. Okay, so this is our objective. What does a cyclone look like when we're looking at reanalysis data? On the left, this yellow circle in the star is an identified cyclone from the tracker. And on the right is the snowfall data from ERA interim. And you can see if we just went with the yellow circle, which is the size of the cyclone that the tracker identifies, it doesn't capture all the precipitation with that cyclone. So we increased this radius by 2 latitudinal degrees so we can better capture the precipitation associated with that event. It's not perfect. There are better ways to do that. And if you're interested, I can share those with you later. But that's what we did for this analysis. And it's good to keep in mind as we go through the results. All right, so let's go through the snow data first. And then I'll walk you through the cyclone data and how they relate to one another. Okay. For snow, there's a very big difference in the distribution of it across the Arctic. We have a lot of snow in the Atlantic throughout the seasons, and there's a lot more snow accumulation in the Atlantic throughout the seasons. So what's the difference between snow depth and accumulation? Depth is what's happening over time. It's a cumulative amount. Accumulation is the difference between the first and last day of that season, so how much fell within that period. And what we find is the timing of when most snow accumulation occurs can differ between regions, and also the snow depth can differ between regions. So I'm going to make this comparison between the Atlantic and the Pacific. And what I mean by that is this area that includes the Chukchi Sea, the East Siberian Sea, and Beaufort Sea as the Pacific sector. And then the Atlantic is the Greenland Sea, Karen-Barents Sea, and parts of the Lincoln Sea. And if you're interested in these regional differences, I have a time series on the bottom that you can look at. So how does this relate to, first, the number of cyclone events that happen, and then the intensity of the cyclones? Well, for one, there's a lot more cyclones in the North Atlantic than anywhere else in the Arctic. But it turns out that they don't have a strong effect on the variability in snow accumulation. So from month to month, these cyclone events aren't really contributing much to the snow accumulation. So when we look at intensity, it's a similar story, but there is a stronger relationship with intensity. It's the same regional pattern and same seasonal pattern, but really it's not the dominant factor that controls or that influences snow accumulation on sea ice. One interesting result that we found from this is, although there are fewer cyclone events in the Pacific, we found that the snowpack is much more sensitive to the intensity of these cyclones than their frequency. So what does that mean? It means if you're in the Pacific area of the Arctic, you can have a lot of cyclones and the snow depth may not change all that much. But if you get a really strong or really weak cyclone, that will have a long-standing effect on the snow accumulation in that region. So that's the number of cyclones and the intensity of cyclones. The last characteristic I wanted to evaluate was cyclone snowfall. And here we found that there was a really strong relationship between the cyclone snowfall and snow accumulation over time. What's really interesting to me is this difference between the Atlantic and Pacific again, where the fraction of the total snowfall comes from cyclones is 83% in the North Atlantic. That's a huge number, whereas it's only about half in the Pacific. So this means that there must be other mechanisms that are important for snow accumulation on sea ice there. This can be snowfall that comes in the form of diamond dust or polar lows or other types of frontal systems that transit this region. But for the North Atlantic, it's really all about the cyclones that transit there that control what's happening, that controls the snow on sea ice there. Okay, so yes, cyclone snowfall is very important. But what about freeze-up? In that earlier study, I showed the trend in snow depth on sea ice in the Western Arctic was strongly related to the timing of when sea ice forms. So which is more important, sea ice freeze-up or cyclone activity? And that's what I'm showing here. In this upper plot, these are the correlations with monthly snow accumulation. And it can be cyclone count, it can be cyclone snowfall, it can be a combination of counts and snowfall and intensity, but across the board what we found is there really isn't a strong relationship except for cyclone snowfall and these other factors, especially when they're combined. And what I'm showing on the bottom here are these correlations between the timing of sea ice freeze up for different regions of the Arctic. What we found is it's roughly comparable. So the timing of sea ice formation is important, but so is cyclone activity. It's about roughly comparable. So you can't really say that it's one or the other. And you also can't say it's just those two factors that influence snow on sea ice. It's not a correlation of one. There's obviously something else going on, or there's something that we're missing in this analysis. And I think that's important to consider both. Okay, so we were motivated by this pattern of snow accumulation on sea ice in these two different regions, and we wanted to know, is this analysis, coming up to match with the buoy data? Does this make sense? And when we ran the tracker on these same areas that the buoys were drifting, we found that, yeah, actually they make a lot of sense. We found that less than half of the accumulation events in the Pacific were associated with cyclones, and a larger proportion in the Atlantic were found, but not nearly 83%, but definitely more than half, 64%. And overall, this really points to the differences in the atmospheric processes between these two regions. In the Pacific, you have weaker storms, so you can look at the sea level pressure of these two buoys, and there's definitely lower pressure associated with these cyclone events in the North Atlantic compared to the Pacific cyclone events. So again, this means that there are other mechanisms that may be important for this Pacific region. It also may be a fact that we're missing all of the, not all of, but part of the snowfall associated with these cyclone events. I said that we took a larger radius. Well, maybe that's still not getting all of the snowfall with these cyclones. That's something to build on for future work. Okay, so that's enough about the relationship between cyclones and snow on sea ice and how they relate to one another on a regional scale. What about the long-term trends? We talked about this bottom-up effect affecting snow on sea ice, but is there a top-down effect? Could changes in cyclone activity be changing what is going on with snow on sea ice? So on the left is the trend in snow depth over time from that reconstruction approach. And if you can see, it might be a little tricky, these gray areas are areas of statistical significance. And this is really interesting to me because we did find some positive trends in snow depth on sea ice. And these were associated with areas of the old ice or ice that survived multiple years, multi-year ice. And they were also associated with an increase in cyclone counts, intensity, and snowfall, although these were not statistically significant, so you can just ignore what I just said. For the negative trends, though, these were statistically significant. They are associated with later and later sea ice freeze-up, especially in the Kara and Barents Sea, which is in this region, and in the Chukchi Sea, which is here. And a lot less snowfall and more rainfall. So I thought that was really interesting that it's really a mixture of both atmospheric processes and sea ice formation that's driving these negative trends. I think for the positive trends, there's a lot more to unpack there, and this is an area that could do with a lot more research. So why are there differences here? Why don't the trends agree with the observations? We found a decrease of 3 centimeters per decade, and the reconstruction isn't even showing a 1 centimeter per decade decrease. Why do they differ? And this goes back to how we can bring models and observations together in a coherent way. There are many reasons that these may differ. It could be the observational uncertainty, missing processes in this reconstruction approach, and also uncertainties in the reanalysis products. So going to the observational uncertainty, the observed trend was based heavily on this data from a snow radar attached to an aircraft. And recent work has shown that the radar is actually quite sensitive to how much salt is within the snowpack on top of that sea ice. If there's a lot of salt that's wicked up into this snowpack, the radar is going to have a shallower return. It's going to underestimate how much snow is actually there. And this occurs over first year sea ice. So that may mean that we're not getting the true trend of snow conditions in the Arctic. We may be overestimating the trend in snow loss in the Western Arctic. And I should say that there are multiple products, snow depth products from this snow radar data, and the majority of them have this issue. On the other side of this is these snow depth products don't always capture thin snow. Some will omit any snow that's less than 8 centimeters thick, so they can be biased in that sense. So really, it's important to take the caveats of an observational data set on board when you're evaluating trends or using them to evaluate a model with. Okay, and another caveat to consider is even though you can make a comparison with observations, just one comparison isn't enough, oftentimes, again, because of how unique an environment is. Okay, so what about these missing processes? And one thing that I've been circling back to is this idea of summer snow, and I've talked to a few of you about that today, is we really don't know how much snow there is on sea ice during the summer period. What I'm showing here is an old figure hand-drawn from the climatology, from the drifting ice station data from the former Soviet Union. And in the very central of the Arctic, they're saying that there's about 2 weeks where there's no snow. The rest of the year, it's completely snow-covered. And since then, several people have assumed that it's completely snow-free because we have melt pond data that suggests that there are melt ponds there, and it would be difficult for melt ponds to exist with snow when it's that warm and things are melting that rapidly. But we really don't know how much snow is there. And when we make these comparisons with the airborne observations and the model data, they're not in full agreement until we put an initial snow depth there, something that's there in August. And so I think one thing to look at in the future would be, can we nail down how much snow is there in August or in July? And this has a lot of important implications, not just from an albedo perspective, but from a satellite perspective too. It affects how we derive sea ice thickness. If there's snow there, and it's not sea ice, it's going to throw our derivations all off. So yeah, that I think would be an exciting area of research to expand on. And okay, reanalysis products, these are hard. And the reason these are hard is they differ so much depending on which one you use.
Maybe you might want to explain what a reanalysis product is, just to
oh, yeah. Yeah. Yeah, thank you. So a reanalysis product is a product derived from model data. The model is running and outputting all of these variables that represent our environment. So it can be rainfall, snowfall, cloud cover, etc. And they're very sophisticated models, but they do have to simplify how processes are represented. And it's not just one model doing this, it's many different models, and they differ in how they treat their physics. And therefore, their output's very different from one another. So in this nice paper by my colleague Lynette Boisvert, we did an intercomparison of different snowfall products from models, and we found that they differ by quite a bit. This is the number of days in the year that there is snowfall from these products. And the numbers aren't so important as just the difference in the colors. That gives you a really good idea. The color scale is to 350 days, that there's a huge difference and we don't know which one is right. And we don't have enough observations of precipitation to know which one is right. So these results are really sensitive to the reanalysis product chosen. We chose one that is in better agreement with our observations, but again, I don't feel super comfortable in saying that because we don't have a lot of observations to say that's really the case. So why are these so different? I talked about their different treatment of physics. Also, these models are assimilating data, and depending on when new data sets come online, this can create a change in the trends or a change in their output. And also, as they make improvements to their model physics, this can create erroneous trends. So an example of this is how precipitation is partitioned into the liquid and solid phase. If you change that midway through your time series, you'll have a very different trend for that later portion of the record. So these are really problematic, but it is the best thing that we have because we don't have any full coverage data set of precipitation, and this is why we use it. Okay, so that kind of wraps up this portion of the presentation. The main takeaways from this work is which processes dominate. Is it a sea ice freeze-up or a bottom-up effect, or is it cyclones, a top-down effect? And what we found that cyclone snowfall is really important for the variability in snow on sea ice, but there are really large regional differences. So I kind of hate using an Arctic average because that's not really representative of any one region. It's really helpful to break it down and zoom in and take a look at what's going on in a specific region. Similarly, with sea ice freeze-up or the formation of freeze-up, that was equally important, but again, there are some pretty large differences depending on which region of the Arctic you're in. We found, for example, in the Laptev Sea, there was hardly any correlation between snow and sea ice freeze-up. But in the Barents Sea, it was nearly half. So, and these are not too far from one another, which I think is really interesting. We found that, okay, cyclones are indeed important for snow accumulation on sea ice, but we also found some nuanced results from this. The Pacific was more sensitive to how strong or weak the cyclones were. Cyclone Snowfall made up a much larger proportion of the snowfall in the Atlantic region than the Pacific. So this makes me think that there's a lot more work to be done in understanding what's happening in the Pacific, because it seems very quite different from the North Atlantic, the interactions between the atmosphere and snow cover there. Okay, so I've presented this work, but that really doesn't get to the question that I posed initially. Is snow good or bad for sea ice? This gives you an idea of how it can be good or bad for sea ice, but how are we going to address this question? And to be honest with you, the only good tool for this is an Earth system model, because it's fully coupled to the atmosphere and the ocean, so these different components can interact with one another. So what I'm showing next is preliminary work, and I would love feedback if you have any insight on how to interpret some of this data, because it really is early work, and we hope to be wrapping this up over the next 6 months. First, we're going to assess an Earth system model, and I'm going to provide some suggestions on how to do that in a safe way. It's really easy to overlook what an Earth system model tells you, but there are some really scary things that an Earth system model can do, but some really amazing things that it can do as well. And then we can get to the projections and the experiments of the model. Okay, so the two models I'm working with are from the National Center of Atmospheric Research. This is the Community Earth System Model, CSM1 with the CAM version of the atmospheric component, and then CSM2 and WACM2. So I'm not a modeler, and I don't know how to explain this really well, but my interpretation of these differences is this is the old version of CSM1, this is the brand new version, and this is the brand new version with a really fancy atmospheric model, and that's the best of my knowledge. Okay, so the fancy version of the atmospheric model has more vertical levels of resolution and aerosols and things like that, but really that's the limit of my knowledge on it. And so I was curious to know, how do these models compare to the observations? And the easiest start to do this is to look at it qualitatively. Forget the numbers, just how does it look? Is it getting the spatial pattern right? And what was really interesting to me is there's a whole lot less snow in the new version of the model compared to CSM1. You could say that CSM1 is actually maybe doing a better job than the newer version of the model. But we can't just go by qualitative comparisons. We have to go beyond that. And before, a lot of people would just take an average of the Arctic and make that sort of comparison. But that's not great to do. As we saw, there are some pretty large regional differences in snow conditions and ice conditions. So what we're doing is evaluating this in a regional perspective, similar to how we did the cyclone analysis. But we're also evaluating it based on the ice conditions. So the model outputs these subgrid scale ice thickness categories. So within a model grid cell, you can have 5 ranges in ice thickness. And you can pull the snow depth distribution from each of those 5 thicknesses and compare it to the observations in a comparable way. So that's where we're going next with this. I'm sorry I don't have a figure of it, but maybe next time I can share that with you. But okay, say we've assessed it. We know what the uncertainty is. Let's go to the next step. And honestly, I haven't finished assessing it. I was just excited to see what the results would be. So I'm going to run with the CSM1 version with CAM and show you what the future changes in snow are like in relation to the future changes in sea ice. Now, I'm taking daily averages of the large ensemble here. So there are 35 ensemble members, and what that means, my interpretation as not a modeler, is there are 35 virtual realities, and these are representing the internal climate variability of this Earth system model. So I've averaged these, and I'm taking daily averages and looking at changes in ice area, ice thickness, snowfall, and snow thickness over time. So the big thing here is, yes, there's thinner snow, and this coincides with later sea ice formation. But what's really interesting is the changes in the snowfall. So there's a shift in the snowfall pattern here. More and more snow is happening later and later in the winter season. So even though there's later sea ice formation, you're still getting snow on sea ice, but it's still thinning over time because you're missing the sea ice platform. It hasn't yet formed and it's still missing a lot of this snow. What we found was snow-free conditions in summer precede ice-free conditions by at least 30 years. So what's the positive of this? Like I mentioned before, if there's snow or if the snow is very thin, ice can grow rapidly, and we do see that. When we look at the ice thickness in the fall period, you can see this is fairly gradual slope of ice growth, but here it's much more vertical. That means the ice is growing much more rapidly, but it's not enough to offset the loss of sea ice or the melting of sea ice in the spring, and this has a lot to do with thinner snow in the spring. The thin snow in spring doesn't explain all of it, but it does explain some of it. Okay, and I am almost out of time, and the last thing I want to show is snow processes. So we have this question of, if ice is thinner and there's more snow being dumped on it in the wintertime, could the snow be so thick and heavy relative to that thin ice that it depresses it into the seawater and it floods and freezes? This is a pretty unique process in the Arctic, but it's really common in the Antarctic. It's a way that ice can grow thicker fairly rapidly. And we wanted to know, is this going to be a process that becomes more and more common as ice thins? And so we looked at the snow mass budget in the Arctic over time, so the 2000s to 2030s to 2060s. And what we found was, no, the snow ice formation isn't more common over time, even though the ice is thinning and even though this snowfall cycle has been pushed back. There wasn't really any meaningful changes in the sublimation or the dynamics of snow. So when I say dynamics, that means ice is ridging and some of the snow goes into the water when ice collides. And we also saw there was much earlier spring snowmelt, which affects the ice albedo feedback over time each summer. That may partly explain why we have greater ice loss in those later years. So if you were to ask me, is snow good or bad now, and is snow good or bad in the future, I would suspect that it becomes a more and more net negative effect over time, but I'm saying that with a caveat because the analysis is not yet done. Hopefully I can put together a paper this year and tell you the result. So thank you very much for listening, and I'm happy to take any questions.